Okay, great. So for our second talk, we have Alex Cowan, who's going to tell us about computing modular forms using supersingular isogeny.
Thanks very much. So some thank yous. Thank you to Noah Melkes and Kimball Martin for lots of incredible guidance. Thanks to Aranisov, David Rowe, Drew Sutherland, John Voight for lots of really helpful conversations. Thanks to Oklahoma University for running the code, and thanks to Simon's Collaboration for funding. So this talk is going to be about an algorithm, and I'm going to talk about what the algorithm is doing, how it does it, and then what it spit out. So this algorithm, it's primarily an algorithm for computing Q expansions of weight 2 modular forms, prime level, and degree 6 or less. That's all, it's all trivial character. It does one bonus thing, which is it checks that there's only one modular form of degree 7 or more for acular eigenspace in this setting of prime level. So we're only going to be missing one thing per acular eigenspace. And here I'm using the term the degree of a modular form. I'm going to say that to mean the degree of the number field that its Hecke eigenvalues generate. This is sometimes called the dimension of a modular form, but I'm going to call it the degree here. And this number field is sometimes called the Hecke field of the modular form. So I said this is an algorithm for computing Q expansions. What does it mean in this context to compute a Q expansion? What objectives are we going to have for this algorithm? So there are going to be 3 objectives. The first one is we need to compute enough eigenvalues to say, okay, we've computed the modular form. And in this context, this means up to the Sturm bound. So there's a theorem of Sturm that says that if you have 2 modular forms of level P, and they agree to the first P over 6 Fourier coefficients, then in fact, they will agree forever. You have the same form. So we're going to compute up to there. The second objective that we're going to have is that the algorithm, we're going to want it to run quickly. So quickly in this context means we want to take time level squared to compute all the modular forms of that level. And for the space requirement, we're going to want to be quasi-linear in the level. So the time requirement is because there are already great tables of modular forms out there on the LMFDB. And to go further than that, we need a really fast algorithm. So level squared is going to be our benchmark. And then the space requirement is purely practical. If you use more space than this, your computer's going to run out of RAM. So that one's easy. And then the last objective that we're going to have is we want to compute complete tables of modular forms. And this is just because when you have a bunch of data, you can do a lot more with that data if you can guarantee that at least in some stated range, you're definitely not missing any Q expansions. Because if you were missing some Q expansions, I don't know, it's a lot harder to use. Unfortunately, this ends up not being feasible. So typically, as a way to see how it's unfeasible, typically what happens is that in every acular eigenspace is just one big Galois orbit. So the Hecke eigenvalues are going to be degree P algebraic integers, and we're going to want about P of them up to the Sturm bound. So that's already P squared information. And we said space requirement is quasi-linear in P. So already we see that we're going to run into huge problems, and the problems just get worse from there. Right? This is really sort of not doable. So instead, we're going to compromise. We're going to say that for one modular form per acular eigenspace, we allow ourselves to write down just a trace of that modular form. And then for the rest, we'll compute the full Q expansions. Okay, so that's what the algorithm does. How does it do it? So it's a long and technical algorithm. There's a paper that goes into really gory detail, and it's disorienting because it's so technical. So here, I'm really aiming to try and give some sort of overview to sort of help you find your way around this paper if ever you want to check it. I wish I could start by saying, there's this one key idea and the whole algorithm is doing that. And there is such a key idea, but unfortunately, it's going to have to wait 2 slides. So the beginning of the algorithm and sort of the whole algorithm is based on manipulating supersingular isogeny graphs. So in supersingular isogeny graph, you have a bunch of supersingular elliptic curves in characteristic P, and the edges are going to be L isogenies. For what I'm doing, L is going to be 2 almost always. And with this supersingular isogeny graph, the main point is that there's this theorem of Mestre, which says that So on the left-hand side, you have this f of q. And this f of q is the q expansion of a modular form of level p. And on the right-hand side, you have this x. And this x is an eigenvector of the adjacency matrix of a supersingular L isogeny graph. And Meshra's formula, so this is the whole point of the algorithm, is computing, telling you that if you compute this right-hand side, if you can find this eigenvector, because that's the hardest part, then you can use that to basically get your Q expansion immediately, right? It's just this Q expansion times some constant. So the whole algorithm is going to be about computing this right-hand side from Meshra's theorem as quickly as possible. So the hardest part of computing this is in finding this eigenvector x, right? This eigenvector that's an eigenvector of the adjacency matrix of the L isogeny graph. Linear algebra, if you do it naively using algorithms taught in the first course in linear algebra, it takes time matrix size cubed. And the main speed up that we're going to get, the reason that this algorithm runs quickly and the bottleneck comes from using Wiedemann's algorithm and doing all this linear algebra in time p squared instead of p cubed. Here I'm saying p because the matrix size is proportional to the level. So Wiedemann's algorithm has some caveats for our use. The first caveat is that we need a sparse matrix. That's no problem. Our matrix is already sparse. The second caveat is that we have to work over a finite field. And Meshra's formula isn't characteristic zero. It's not over this finite field. And Wiedemann's algorithm is so great that what we're going to do is we're just going to pick some arbitrary small finite field. Here I chose f1009, completely random. And we're going to do everything mod 1009, and then we're going to figure out how to lift it back to characteristic zero later. So, and then the third caveat for Wiedemann's algorithm is that it gives you the minimal polynomial of your matrix. It doesn't give you the eigenvectors, which is what we want. It turns out that that's really not a big deal. Once we have the minimal polynomial, we can just do a little bit of extra work and get the eigenvectors without too much trouble. But one caveat for this part, for this sort of way to mess with Wiedemann's algorithm to get what we want, is that Wiedemann's algorithm is random, meaning that it takes some arbitrary input and then output something, and it's not at all clear how you go from the input to the output. And it is guaranteed to give you a divisor of the minimal polynomial of your matrix, but it does not guarantee that you will get the full minimal polynomial. You almost always get the full minimal polynomial, but it's not guaranteed that you'll get the full minimal polynomial. And one of our objectives, if you recall, is that we wanted complete tables of modular forms. So we can't accept this chance that the algorithm fails silently, because who knows, maybe we miss a modular form that way, right? That's no good. So one of the biggest parts of these modifications to Wiedemann's algorithm is finding a way to make sure that we've actually gotten the full minimal polynomial and not just some proper divisor. So it's technical and the details in the paper, but that's maybe sort of the biggest change to the algorithm.
You know the degree of the thing you're looking for, right? So that's not.
Well, so we know the degree of the characteristic polynomial, but not the minimal polynomial. So indeed, that is how this works, that we're going to modify Wiedemann's algorithm so that we get the characteristic polynomial, and then we can just compare degrees and see that we got it. Okay, so at this point, using Wiedemann's algorithm, we get an eigenvector over this arbitrary small finite field, and we're going to have to lift it back to characteristic zero. And the way to do this, I think that the easiest way to explain how this goes is just to give an example. So let's say that we get this eigenvector that's the first row of this table, mod 1009. So 308, 0308, 701, 393, 0308. The key idea, the heuristic, is that over the integers, probably the most common entry in this eigenvector is going to be 1. We don't know that for sure, but probably that's true. So we're going to take this eigenvector, mod 1009, and we're going to rescale it so that the most common entry in that is 1 as well. And so if you divide by 308 here, then you get 101, 1008, 1701. And now, okay, if you want to lift to the integers, well, this 1008 sure looks like it wants to be -1. This 1007 sure looks like it wants to be -2. And so you get some vector over the integers. And we don't know for sure that this is an eigenvector, but we still have this adjacency matrix of the supersingularized Hodgkin graph. We can just check that it's whether or not it's an eigenvector. And it almost always is. When it isn't, do the same thing, but guess that the most common entry is going to be 2 instead of 1, and keep going until we find it. And this always works pretty quickly. If your eigenvector isn't defined over Q, but instead over some extension of Q, or if you have repeated eigenvalues, then it's the same idea, but it's a lot more technical. But it's always the same idea that the most common thing you're going to see in characteristic 0, the most common entry, is going to be small in some sense, and just you want to rescale things such a way that it's going to be small, and then you'll have a sort of a quote unquote obvious lift. So okay, we do this, and we've got our eigenvector x of the supersingularized Hodgkin graph adjacency matrix. And that was definitely the hardest part of computing this right-hand side. And so we're more or less home free at this point. We just need to deal with these power series. This J is the modular J function. And we need to deal with the sum over the supersingular elliptic curves. But the hardest part is definitely behind us. So all 100% of the time spent in the algorithm is in doing the linear algebra. It's in finding this this x, right? This eigenvector, and then the rest of it takes a negligible amount of time. But it's only negligible if we do it properly. If we did it in the most naive way possible, then it would actually end up taking also about time p squared, but with a much greater constant. It would be almost all of the runtime. So the way to deal with this right-hand side, or the remainder of this right-hand side quickly, is using these standard tricks that, it's nothing new, but it's stuff that people should definitely be aware of, is very useful. These tools are very useful and can be used in a lot of situations. So the most important one is definitely using the fast Fourier transform. That just gives you a huge speed up whenever you're doing manipulations with power series in characteristic P. And the second thing that we're going to need is we're going to need to get the Q expansion of the modular J function mod P. And to do that, the way I chose to get that was to take the weight 12 classical Eisenstein series and to divide by the cube of the Dedekind eta function to the 8th power. So you can divide by, say, the discriminant if you want, that's fine. But dividing by the cube of the Dedekind eta function to the 8th power ended up being slightly faster in practice because the cube of the Dedekind eta function has a Q expansion, which is quote unquote sparse, right? Most of the Fourier coefficients are 0, so it ends up being slightly faster to divide by that instead of something else. And then you have to fix the constant term. The next semi-tricky part of manipulating this right-hand side is that we have the sum over the supersingular elliptic curves, so about p of them. If you did this naively, it would take time about p squared, and it would be sort of big p squared. Instead, you can use this binary tree structure idea. So you take your sum, you recursively split it into half sums, and you leave J as a formal variable for now. Don't substitute in the Q expansion yet. And at the bottom of the tree, the top of the tree, whichever way you want to look at it, you'll have a lot of sums, but they will be sums of very low degree rational functions in J. And then as you go back up, you're going to have higher and higher degree rational functions, but you're going to have fewer sums to compute. And these two factors balance each other out. And you don't have very many levels in this. You have about log p levels. So this takes something that would have been time p squared naively and reduces it down to about p log p. And then after doing that, you get one big rational function in J, and you need to substitute in this Q expansion. And for that, there's an algorithm for power series composition by Brent and Cohn. And this ends up being the longest part of this part of the algorithm. It takes time p of 3/2. And you can see that this is nothing compared to the p squared that we spent already on the linear algebra. So this part is fast as long as you are aware of the standard tools and do it properly. Okay, so at this point, we've computed this right-hand side, right? We got the eigenvector from Biedermann's algorithm, and we did everything else carefully. And then this left-hand side is exactly the Q expansion that we wanted to compute. So we're done. We have our Q expansions. At this point, we could just stop and we could declare victory. But there's sort of this pending, sort of looming question of, are we missing any bigger degree forms? Maybe there's a degree 7 form out there, and this had only computed the forms up to degree 6. So maybe we're missing something that we shouldn't really be missing, right? We said that we can have one form for acting on our eigenspace where we just write down the trace, but for a degree 7 form, we should really write down the full Q expansion. So how do we know that we're only missing one form for acting on our eigenspace? This is definitely the hardest part of the algorithm. It takes much longer than anything else. It's completely optional. I mean, the output is yep, there's nothing there. So, but it's it's good to do it. So the plan, well, so the plan comes from this this straightforward observation. What we're really trying to do is we're trying to look at the characteristic polynomial of, say, T2 and show that it's irreducible in characteristic 0. And this is hard. I mean, we can't even write this down. It'd be too big. The plan that we're going to have is, so if we pick some arbitrary d, just some random degree that a factor might have, say 7, and we look at the characteristic polynomial of T2 mod 1009, and we see that has no factor of degree 7 mod 1009, well then, okay, clearly in characteristic 0, it didn't have a factor of degree 7 either, because this degree 7 factor would have just reduced to a degree 7 factor mod 1009. So the plan is going to be that for every single possible degree that this characteristic polynomial could have, we're going to find some small arbitrary prime nu and show that the characteristic polynomial mod nu has no factor of degree d, and so therefore over the integers it didn't have a factor of degree d either. So that's the plan. This is quite daunting, right? So the first thing that this is going to require, the very first step in this, is we're going to have to compute a bunch of characteristic polynomials, mod a bunch of small primes, and then go and factor them. Previously, the longest part was Wiedemann's algorithm to get one characteristic polynomial, not even factor it. That was 100% of the runtime before this step. So you can see that already this is much more time consuming. And then the second thing that we're going to have to do is, okay, we have a bunch of irreducible factors mod nu coming from factoring, and we have to take those irreducible factors and we need to put them together and see what degrees are possible. Because I mean, because an irreducible factor in characteristic 0 is not necessarily going to reduce to an irreducible factor mod nu. So there's no word irreducible here, right? It's just factor. So this is somehow even scarier than factoring all these characteristic polynomials. So the factoring, if you go and you look up what it says that factoring in this case would take time t cubed, which is too long. Right? We said we wanted everything to run in time p squared. However, in practice, heuristically, what happens is that the longest part of the factoring algorithm for polynomials over finite fields is if you have a situation where you have a bunch of irreducible factors all of the same degree, and then untangling them takes time t cubed. But we have basically random polynomials in this finite field. You're not really going to have these huge coincidences where you have just a bunch of different factors, irreducible factors at the same degree. So maybe you'll have like a dozen somewhere or something, but nothing at all daunting. And this never really happens, but in principle, if you were really running into trouble and something was taking forever, you can also just give up on that one nu, right? These nus are completely arbitrary. So if one's taking a long time, just move on to the next one. That'll solve all your problems. So in practice, this ended up taking time p squared, not p cubed, because we could skip the hard part of the factoring algorithm. And then the second problem, taking all the irreducible factors and turning them into just all the factors that are possible. This is a well-known problem in computer science called the sum set subproblem. And it's known to be NP complete, right? So here we're really not going to get a polynomial time algorithm, except there's a dynamic programming solution. And in our specific case, that runs in time p squared. And this is basically through shear luck. And the reason why this doesn't truly count as a polynomial time algorithm is because the runtime depends on the size of the terms that you're summing up. And that's sort of not really the problem statement of the general subset sum problem. You're not allowed to really depend on that, so it doesn't count as a polynomial time solution in general. But for us, it runs in time p². So that's very lucky. And then there's some extra tricks and some optimizations you need to make, but ultimately this does run. You can actually make this plan work. So we went and we did check that there were we weren't missing any high degree modular forms with this strategy, which is, I was a little bit surprised that this worked, but okay. So that's the end of the algorithm, and it's a lot, right? It's a ton of information. What should you remember from all this? What are the most important things to keep in mind as you come away from this? Well, the whole algorithm is really about meshless formula, right? The left-hand side was the Q expansion, the right-hand side was that thing with the eigenvector. The whole algorithm is about evaluating the right-hand side of meshless formula. The second thing to remember is that the main reason this algorithm is fast, the main reason that we got Q expansions that hadn't been computed before, is because Wiedemann's algorithm is really fast. It's just a great algorithm. So the thing to remember is that we had some tricks to lift these eigenvectors back to characteristic 0. And the fourth thing to remember is that all these standard power series tools that, it's nothing new, but is really important to be aware of them because they're just so useful in so many different situations. Okay, so at this point, it's time to talk about the results. And so this section, it only has one slide. It's this huge table, so I'm not gonna touch it. But so what the code that we ran it up to level 2 million. So the LMFDB ended at level 10,000, and so we extended that to 2 million. Up to level 1 million, we did this verification that there are no extra modular forms of degree 7 or more. For 1 million to 2 million, we didn't do that verification. So yeah, there could be. And then I split up the table in this way because these three columns. This column is telling you how many appear in the LMFDB. This column tells you how many forms we got between when the LMFDB ends and 1 million, and then this one is between 1 million and 2 million. And this G, this is the degree of modular form, and this delta is the discriminant of the Hecke field, of the number field that its Hecke eigenvalues generate. And then I list some levels where those forms appear. Sometimes it can be interesting when there's only one form. It can also be interesting, for example, in this case, where there's only one example of Q²3 of prime level in the LMFDB, and then as soon as the LMFDB ends, you start actually getting a bunch. So that's sort of a funny coincidence. I split it up this way because one question I'm personally quite interested in is how many of these forms are there? How many should we be expecting? So this first row, these are elliptic curves, and they're great. They're the Brumer-McGinnis-Watkins conjectures for that, or heuristics, that tell you that you should have about x to the 5/6 elliptic curves of conductor up to x. And this is extremely convincing. The reasoning is very solid, matches data very, very well. So everyone believes these. But then for degree 2 or more, as far as I'm aware, so I've never seen anyone actually conjecture anything. And as far as I'm aware, no one has any idea what the correct answer even is. I think that's really interesting because it's such a cool, interesting, and well-studied problem for elliptic curves. But this is a very, I think, natural generalization, and no one knows. So that's so cool. Okay, that's the